We have our first talk is Simulating the Diffusion of Protons in Amorphous Silicates by Liam Morrissey. Take it away, Liam.
Sure, I'll just share my screen. If you can just let me know if you're able to see that working, that'd be great. You're able to see that?
Yep, looks good.
Okay, great. Well, then I'll get started now. All right, so hi everyone. My name is Liam Morrissey, and as was just introduced, I'll give a talk today on simulating the diffusion of protons in amorphous silicates. So what we're going to do here is I'm going to begin with a background. So basically, the sun emits a stream of charged particles known as the solar wind. And this solar wind is comprised 95% of H plus and 5% He double plus. Now, unlike Earth, the lunar surface is constantly bombarded with this solar wind with very limited protection. Furthermore, recent OH discoveries on the moon have suggested that solar wind H implantation and its subsequent diffusion is a key precursor to both OH and water products. However, we do need a better understanding of H retention and H diffusion mechanisms in order to improve these water production models. Now, common statistical-based models, and these are the models that you'll often see used, what they do is they assume various activation energies and diffusion coefficients. Now, in contrast, we can use molecular dynamics, or MD, to actually investigate the diffusion on the atomistic scale. The benefit of this is that when we run these, we're actually simulating the process on the scale in which it's happening. Now, previous MD works on H diffusion in amorphous silica have had a large discrepancy in the previously predicted H diffusion coefficients. So you can see in the table on the bottom, we have a range of orders of magnitude of about 5. And this is a problem because if we want to rationalize that we can use MD, we're going to need to rationalize why we're seeing such a large range in predicted values for simulations that look very similar. So basically what our purpose was that we wanted to investigate the source of these discrepancies in previous MD studies. And then after doing that, we wanted to use MD to better explain the mechanisms of H diffusion in amorphous silica across a wider range of temperatures, which may be relevant for lunar surfaces. Now, briefly, what our methodology was that we used MD to simulate the movement and interactions of all atoms in the system by taking a periodic amorphous silica slab and preparing it to the desired temperature using a reactive interatomic potential. Now, we decided to use an amorphous structure because we wanted to mimic the weathered glassy silicates commonly found on the moon. After we developed our amorphous structure, we then added the H atoms and we tracked the individual movement of each atom for 10 times longer than previous studies. And that worked out to about 4,000 picoseconds. And I've bolded that because I'm going to talk about that later, but I want to just kind of flag it for you. Now I'm going to move into our results. So first, you can see on the right, we have a standard Arrhenius plot, which we can use to track the diffusion coefficients and the activation energies. Now, we actually observed 2 activation energy regions, one in the low temperature region between 100 and 450 K, and one was a higher temperature region. Now, previous similar studies on H diffusion in silicates have also observed these regions. But what's interesting is that this study said that the movement or the diffusion in that low temperature region was actually not diffusion, but only lattice vibrations found at low temperatures. The problem is that while these studies made this finding, they didn't actually investigate the mechanism of the diffusion and were unable to answer the question of, are we just seeing limited motion or are we seeing no motion at all? So basically, we wanted to actually better explain what was going on here by tracking the individual motion of each H atom as a function of time. So when we do this, we can get a better sense of what's going on with the individual movement of each proton within that silicate. So as opposed to the constant motion that you'd expect to see in a diffusion system, we actually noticed that the H atoms instead underwent intermittent jumps from one O to another across the SI-SI midplane. We also noted that the number of these jumps increased with temperature, and we found an average jump size of about 3.4 angstroms. Now, the concept of solar wind implanted H diffusion by jumps was actually first posited in 2006 by Starikina et al. But the problem is because these studies weren't actually simulating the diffusion on the scale in which it was happening, it was only a theory that wasn't actually being shown. So there's still a lack of agreement over whether that was the actual mechanism of diffusion. After showing that motion, we then wanted to find a way to better track diffusion beyond just the MSD. So we actually took these motions and we compiled them into what we call a normalized jump rate, where we actually take the total number of H jumps and we divide it by the number of atoms multiplied by the duration of the simulation. And you can see those findings in the figure on the right. What's important to note is that we did observe a jumping mechanism across all the temperatures studied between 100 to 1500 K. Furthermore, and perhaps even more importantly, we did find jumps in those low temperature regions. Because we're actually seeing jumps from one O to another, this means that diffusion is present at these low temperatures. Now, as we move up to higher temperatures, we obviously see a significantly higher jump rate, which means that the activation energies are significantly less influenced by the lattice vibrations. Basically, what these findings highlight is the importance of considering the individual atomic motion and not just the net MSD at the end of the simulation. Finally, we actually wanted to compare these findings to experimental methods and other similar models. So you can see in the figure on the right, we have a compilation of various MD studies and experimental works as adapted from Fink et al. The various experiments are found in the small circles. Our MD work is the large black circle, and the other MD works are found in the larger squares. You can see that our simulated diffusion coefficient at 300 K compared very well with experimental H in vitreous silica. And we note that H in vitreous silica probably best represents our system. Furthermore, our results are much more accurate than found in the previous studies. But one thing that we did find interesting in this is that if you look at the bottom of this plot in the light green, you can see that H in irradiated oxide had a far, far lower diffusion rate. And it's important to note that our MD model was actually done on a defect-free lattice. So this kind of flagged to us to want to know what's actually going on here, because we know that H diffusion in irradiated oxide is lower, and we know that if that irradiation forms defects, so we kind of wanted to see whether this was traps. So at the end here, we actually ran some MD simulations to verify H trapping at voids, where we actually took hydrogen atoms in yellow and we placed them at the edge of a void in purple within an amorphous silica at a higher temperature. What we actually found was that the atoms always stayed tracked to the defect, meaning that we actually demonstrated that that diffusion within a defect will be much lower, and that defects created by solar wind weathering would likely further reduce H diffusion in regolith. So I can basically clue up here with a couple of the implications of our findings. First, from an MD point of view, we actually showed that H diffusion in silicates occurs via random H jumps, and this is very different than a constant motion mechanism. So therefore, at low temperatures, these jumps are rare, and we need to simulate for longer. Longer simulations allow for better statistical sampling of jumps and the atomic movement. And as we noted, we simulate 5 to 10 times longer than previous similar studies. We think that because we're simulating for longer and sampling better, we're actually getting a better accuracy. And finally, there's also implications from a lunar point of view. We know that lunar surfaces have a large range of possible temperatures, depending both on the location and the time of day. What this study demonstrates is that H diffusion via jumps does occur at these low temperatures. And because of this slow diffusion combined with traps at vacancies, this means that implanted hydrogen atoms are likely outgassed slowly and can saturate the regolith surface. Furthermore, we know that the solar wind is also comprised of higher mass ions that have a larger energy during impacts. These impacts may potentially be leading to temporary high temperature spikes within the regolith that may also be further driving diffusion. And this is kind of our ending concept teaser that we actually want to look at in a further future study. Thank you for listening. And does anyone have any questions?
Yeah, if there are any questions for our speaker, we have a little bit of time.
Yeah, and this is Tom Orlando. That was a really nice talk.
Thank you.
One thing that would be good to point out is the H atom diffusion. When it gets to the surface and it traps,
Yep.
Or it could interact with an oxygen and lead to the formation of an OH. So, and in fact, this is also the mechanism for what people are referring to as OH diffusion.
Definitely, yeah.
Okay, so that's an important point. And these are really important simulations because you're really getting to the bottom of it. I guess the question I have is, the lunar regolith has a lot of other stuff in it.
Yeah.
So what's your next step?
So I think you've definitely gotten to the crux of kind of what we're doing. And with any simulation, especially in MD, you kind of want to start with the best thing you can represent, and then you want to layer in complicating factors so we can continue to get more and more realistic. So basically, I assumed it's an amorphous silicate, but we know that within that amorphous silicate, first off, there are going to be other elements because it's likely more like a feldspar or an albite or a northite. So we can change the potential type such that we're simulating a structure that's more similar. And then what I also want to do is I want to layer in defects and boundaries and vacancies such that I can say that this is a weathered silicate and this is a non-weathered silicate. And I can actually understand what's actually going on with the diffusion. I don't think the mechanism will change, but I do wonder if the rates will change with the proportion of defects, as an example.
Okay, thank you, Liam.